Hello and welcome back to the third lecture. So after quite a long time, and I would suggest going through the first two lectures of phase field modeling that I had talked about earlier. And today we'll start by this phase field modeling parameter identification. So I'll be talking about how do you decide on the different phase field parameters like the length scale parameter LC, and of course how does it relate with the material critical energy release rate GC. So to recap, we had learned about the governing equations for the phase field model, and this looked something like this. We had a displacement problem and a phase field problem, right? And for the displacement problem, we had this equation, which was the equilibrium equation with zero acceleration. So it's a static problem. So it's what? It's nabla sigma plus the body force equals to 0 in the domain omega, subjected to the Cauchy's stress equation, which is sigma dot n cap equals to the specified traction on the traction boundary and a specified displacement in the displacement boundary. And the phase field problem, this is the equation where this capital phi was the history field. If you want to know more about the history field, I would suggest going through the second lecture. This capital GC is the material GC and LC is the length scale parameter. And we have the Laplacian of the phase field. Phi is the phase field, if you remember correctly. And this is what it is subjected to, the gradient of phase field dot n cap, the unit normal, equals to 0 in capital gamma. Capital gamma is the crack surface area. Okay, so we had two different problems, the displacement problem and the phase field problem. Now we start with the single element test or the analytical approach. So if you have these equations, now in a one-dimensional setting, you can of course solve for these equations, right? You can solve these equations to get your displacement, get your phase field, correct? So that is what we will do. So we take a single element because, as you know, in every computational verification scenarios, you always start with a single element, either in tension or in shear, it doesn't matter. Usually we do a single element in tension. So we always start with a single element. This is what we assume. We neglect Poisson's effect and this second order derivative of phi. Okay. So this is what our single element looks like. We have a single square element under plane strain tension. So this U bar is your specified displacement, which is tension. Now, assuming these, and in a one-dimensional setting, your governing ODEs, they reduce to these. So essentially this first equation is a reduced form of this equation with zero body force. Okay, so with zero body force you get d sigma y by dy equals to 0, where sigma y is not the yield stress, sigma y is the stress in the y direction. Okay, then this equation is the reduced form of this equation, where we neglect the second order derivative of phi. Okay, so this is what we get. Here I know we have the second order derivative, but you will see how we tackle it. And the Dirichlet boundary conditions and the Neumann boundary conditions, they get reduced to this. Of course, when y equals to 0, your uy will be 0. Uy is the y displacement, and uy at y equals to L is u bar. Okay, at y equals to L, uy is u bar, and y equals to 0, uy is 0. And the Neumann boundary condition, you have d phi by dy at y equals to 0 equals to 0. Why? Because this place is fixed. So there is no crack, right? There is no crack anywhere. At t equals to 0 or at y equals to 0, there is no crack. So essentially the phase field terms at 0 and L will be 0. Okay. So when you solve these equations, you can try it out for yourself. When you solve these equations for u, sigma y and phi, sigma y is derivable from u. So essentially when you solve it for phi and u, you get these expressions. Now look very carefully. Phi is what? Epsilon y square C22. C22 is your stiffness term. Epsilon y is your prescribed displacement. Prescribed strain due to displacement. So your epsilon y will be what? Basically a change of length to original length, or u bar by L or something like that, divided by GC by LC. GC by LC is what? GC is the energy release rate and LC is the length scale parameter. Plus again this term again. U is what? U is y by this term root under 6 C22 into root of GC by LC. So y is what? Y is the distance along the y direction. And so how do you solve for sigma y? Basically what you do is you have the expression of psi. Psi is what? The strain energy of the cracked specimen. Okay, look into the previous video for this expression. In one dimension, this psi expression will be very simple, and you neglect this as per our assumption. So essentially you have 1 minus phi into psi minus GC by 2LC into phi equals to 0. And from this expression, you solve for phi. If you solve for phi, you essentially get this. Okay? And using this, you put this here, because sigma y is again expressible in terms of the strain energies and the phase field. Correct? As per the anisotropic formulation that I talked about earlier. So when you put this expression in this equation, you get this long expression of sigma y. Try it out. If you have any problem, you can always let me know in the comments. So C22, this has its standard expression in terms of the Young's modulus and the Poisson's ratio, and epsilon y, as I said, it is u by L in one dimension. Okay, or rather epsilon y will be u bar by L at y equals to L. Okay, now look at these two plots very carefully. So in this plot, I do sigma y, which is my axial tensile stress, with respect to epsilon y. Okay, epsilon y is the applied strain for different values of GC and LC. So you see this fat red curve has GC of 5 and LC of 0.1. Then you decrease GC by half and you decrease LC by half. Okay, for this blue curve or the cyan curve, let me say. Then you have this green curve where you keep GC constant, which is 2.5 and 2.5, but you double the LC. Okay, and for the last one, you double GC but keep LC constant. So essentially, what are we doing? We are decreasing GC and LC in the same proportion. So we are halving them one by one, or we are fixing one and halving the other one. Okay, so these are two separate scenarios that I am talking about. Understand this legend very carefully. Okay. So when you plot the stress versus strain response, you will see that for 5 and 0.1 you have this fat red curve. Okay. Then when you decrease them in the same proportion, so you have this, the curves overlap. So this is your cyan curve. You can see the red underneath the cyan curve, right? So these two curves overlap. But this green curve, it is less, right? So what are we doing? If this is our master curve, 5 and 0.1, we are halving GC, but we are keeping LC same. So when you halve GC, essentially what you are doing, you are lowering the overall strength of your material, correct? Because GC is a material property. So you are decreasing the overall fracture strength of your material. So as a result, your failure will happen at a much lesser stress. Okay, so that's why this green curve, it falls down, and this black curve, you are keeping GC same, but you are decreasing LC. So a sharper curve, you are essentially making the crack sharper, correct? And for a sharper curve, your yield stress, sorry, your failure point or the peak of the curve, it tends to go up. Okay, that's why you see a rise of this black curve. So we are not concerned about these two curves. Why? Because we are always behind things that match, correct? So we look at this red curve and the cyan curve, and we see that these two curves match. So we are happy. Again, if you look at the phase field versus the strain curves, again, a typical phase field curve looks like this. It goes from 0 to 1, as I said, and it decreases or increases gradually. There is no sharp discontinuity at any point in the middle. Okay. So again, this red and this cyan curve, which is here, they overlap. The green curve, it is here, and the black curve, it is here. The green curve, as I said again, its failure strength is less. That's why it reaches from 0 to 1 faster at a lower epsilon y. So what is the meaning of this shift towards the left? This green curve, it is shifted towards the left, right? So what's the meaning of this? The meaning of this is that the phase field, it goes from 0 to 1 faster. And for this black curve, it goes from 0 to 1 slower. Okay. Why slower again? Because we are decreasing LC and keeping GC constant. And why faster? Because we are decreasing GC and keeping LC constant. But again, when we are decreasing or changing them in the same proportion, these two curves overlap, just like this case. So observations, sigma y reaches the peak value before phi reaches 1 due to parabolic degradation function. Okay. Again, this point, why? Because you see that the curve, it is not linear here. Just before reaching this failure point, it is not linear. This is a well-known drawback of this parabolic degradation function g of phi that we are using. It is what? It is 1 minus phi whole square, right? So due to this parabolic degradation function, this non-linearity comes, but it is very, very subtle, so we don't have to worry about it. Next, this is the main observation. If the parameter GC by LC, we name it as chi, if it is constant, we get the same response. So essentially what? We are decreasing or changing them in the same proportion, right? So this ratio GC by LC is constant, and we name this constant as chi. Okay. So when chi is same, we get the same response. That is why in this expression, you could see we have clubbed GC by LC as a single term. Okay. And this term is really important. You see here also it is clubbed, here also it is clubbed. Okay. Again, here you see GC by LC, it is again clubbed. Here also GC into LC. So again, always GC and LC, they are interdependent of each other. That is what we are talking about in this parameter identification of PFM. Again, the overall GC, we express it as the area under sigma y versus epsilon y. So it is this shaded area. It should be toughness, but again, it is a qualitative estimation of the overall fracture strength of the material. So we kind of consider it as proportional to the overall GC. It does not match with small GC. Small GC means the material GC. So if you take this red curve and calculate the area under it, you will see that the area of this curve and this GC will not match. Okay. So there is a mystery behind it that we will discuss. So We take a representative analytical problem. So we discussed about the single element, correct? So essentially this element pulled by tension and fixed at the bottom was our single element test. Now what we do is we take it a bit further. We have one block and we have one more block. These two are rigid blocks, and there is a small layer in between. Okay, so think of it like this. You take this block and take this block and you stick them together with glue. Again, I am telling it as glue because of, you know, some qualitative stuff, but it need not be glue. You just stick them and then you pull them. You pull them on both sides. Okay, so we take this the thickness of this small layer as L, and this is our axis. Now what about these? What about these? What we do is, since these are rigid blocks and one-dimensional blocks, one-dimensional why? Because we are neglecting Poisson's effect. Because of these two reasons, we can replace these two blocks as two springs with spring constant K. Okay, so we pull both sides by U, but essentially since they are rigid, but this layer is your what? Deformable layer, right? So the displacement of this layer need not be same as the applied displacement. If it is same as the applied displacement, then this layer had no meaning. This layer would also have been rigid. Okay, because it's the same displacement that is passing. But that's not the scenario. Because you are adding a deformable layer in between these two blocks, you have to consider the velocity, the displacement of these 2 points as a different displacement u2 compared to this applied displacement u. Okay. Now we can write this spring equation, P equals to K into u minus u2. So for this spring, it will be what? It will be this. And for this spring also, of course, because they are pointing towards two anti-parallel directions, where K is E by L. Again, from one-dimensional constraints, we can derive K as E by L. Now, you have to solve for what? What is the unknown in this? P, you can always derive it from the applied displacement. K, you know it is E by L. So the unknown is U2. Correct? So how do you solve for U2? U2 will be what? It will be U minus P by K. Correct? U2 will be U minus P by K, where your K is E by L. So 1 by K is what? L by E. So U2 will be U minus PL by E. Correct? We are taking the area of cross section as 1. So our capital A term that typically is here, it is 1. So essentially your U2 will be U minus PL by E. Now, what is this big equation, right? So the term P can be derived from the stress formulas. Okay, so we derived these. We derived this expression for the y directional stress. Correct? Now for one dimensions, this sigma y will be what? This sigma y will be P by A, and A is what? A is L. Essentially A is L. Why L? Because the thickness is 1. Correct? The thickness is 1. So it will be L into 1 or L. So if you replace P by L here, you have P equals to this expression into L. So When you do all of those substitutions, you get this expression in terms of chi. Chi is what again? Chi is GC by LC. Correct? Chi is GC by LC. Now, this expression is only valid for this layer. Okay? That's why in this y is what? This y is the y directional position. Okay? Now in this single element test, we always consider this single block as deformable. Correct? So this y, it will be an integration from 0 to L. Okay? But in this scenario, we are considering the deformable layer as only this smaller layer. That's why your y will be from minus L to plus L. Sorry, it will be from minus L by 2 to plus L by 2. Okay? That's why we have this small l in this expression and not capital L. Because capital L we already know. Now, this is a Newton-Raphson problem. Why? Because in the left hand side you have an unknown quantity, and in the right hand side also you have an unknown quantity. And essentially what you are doing is you are changing this u2. Correct? You are changing the u2. So this u2 will be dependent on u. And we have to solve this using Newton-Raphson. So after Newton-Raphson, we calculate u2 and sigma y using the previous expression for different values of chi. Okay, so this chi or GC by LC is essentially your phase field parameter. This is parametric. Okay, so as and when you change chi, you get different values of u2 and sigma y, of course. Okay, so we vary chi, we get different values of u2 and sigma y. Understand this very, very carefully, okay? Because this is one of the methods how you decide your LC with respect to GC. Okay, you will know the material GC of the specimen you use, but when you are trying to simulate it with the phase field, you always have to determine LC. And that LC you always get it from the material GC. Okay, this is one of the scaling procedures that I am explaining. There are many scaling procedures there. You can always look up in Google Scholar or whatever, and there are many papers leading to this. So after this, you calculate the overall GC, sigma c and delta c. Delta c is this peak displacement. Okay, the displacement at which the peak occurs. So you calculate the overall GC. Overall GC is what? Overall GC is the area under the curve. Okay, sigma c is the critical stress or the stress at failure, and the corresponding displacement at failure for different chi. So this is how it looks like. This capital GC is the overall GC. So this overall GC, when you plot with chi, you get a straight line. So we took quite a number of chi values, and we got a straight line between GC and chi. For sigma c, we got this curve. This can always be fitted in in a regression analysis, and you can always find out an expression for this. And delta c kind of looks like this, which is not important for us. It's delta c doesn't matter for us right now. So the main observation, overall GC versus chi curve is linear. Okay, this is what will help us. So essentially your GC will be what? Your GC will be some slope multiplied by chi plus some constant. So if you know the slope and the constant, you will be able to pinpoint chi, or the other way around. So suppose you know your material GC. This is the material GC. The overall GC is the material GC that you get from your handbooks. Okay, why? That I'll explain. So when you know GC, you will be able to calculate chi using this straight line equation. And again, if you know chi, you will be able to calculate the overall GC. Okay, so we come to the computational solution or the phase field solution. Until here we were doing analytical stuff. Okay, we were playing with equations, we were solving them, we were getting expressions, and then we were just plotting and playing with parameters. But what about a real phase field simulation? Okay, so this one, we take this problem again and we actually solve it in Abacus. Okay, you understood? The previous one was analytical, we were playing with equations. This one is a real computational simulation. Okay, so we take blocks. So the GC of these two blocks, we take it as GC bar. It was 1000 Newton per millimeter. Okay, just an arbitrary value. Okay, the layer, which is this one, this smaller layer, is GC was named as small GC. You remember this small GC was what we varying, and this small GC comes in chi. Okay, now these curves are actual responses from the phase field simulation done in Abacus. Okay, so for this range of displacement, for these different values of GC and LC, we got all of these curves. Now this fact is established that to reach convergence, we have to keep chi constant. So whatever values of GC and LC we use, we have to keep chi constant in order to compare. Okay, so if you see all of these 5 cases, the chi, which is GC by LC, it is constant for all of these 5 cases. Okay, so what is different here? You see, we start with GC as 10, the small GC or the layer GC as 10 and LC as 0.02. So we get this blue curve. Now as you keep on decreasing it in the same proportion, you see we reach convergence. Okay, we reach convergence. So we reach convergence for a GC bar by GC ratio. This is what we call as toughness ratio. Okay, mind you, this is not GC by LC. GC by LC is same for all of these 5 cases. We are talking about the toughness ratio. Okay, so think of it like this. You know the block GCs, right? So this is your bulk material. You know the block GCs from your handbook. Now if you have to have a small layer in between the blocks who has a toughness small GC, how do you determine the toughness of this small layer? Okay, in order to, of course, reach convergence in the phase field solution. So this ratio GC bar by GC is called as toughness ratio. And we saw that this convergence, it is reached for a ratio, for this toughness ratio 800 to 1600. Okay, you have GC bar as 1000, you take small GC as 1.25 and you divide them, you get a ratio. Again, you take it as 0.625, you divide them, you get another ratio. So in between these, we have convergence in the phase field solution. So whenever you are designing any material for failure, which has a layer, a weak layer between them, between two rigid materials, if there is a weak layer, and if you are designing it, you always take into account this criteria. Suppose you have a bar of chocolate. You are designing a bar of chocolate, say dairy milk with two flavors. Okay, say chocolate and something else, vanilla. Now these two blocks are made up of chocolate that you know. Now, how do you optimize the toughness, or toughness? Yeah, the toughness of the vanilla layer, which is supposed to be in between, such that this thing, it does not break. Okay, so this is the kind of problem that we are dealing with, and for that you have to take into consideration this convergence criteria. Okay, so if we take this criteria and our curves have converged or collapsed into a single master curve, we can safely say that the blocks govern the overall GC. Okay, so for these curves, if you calculate the overall GC, you will find that it is more or less close to the block GC itself. Okay, so we can safely say that the overall toughness of the entire specimen is governed by the toughness of the bulk material. The bulk material is what? These two rigid blocks. Okay, and they have their own toughnesses, GC bar. So this GC bar, the bulk toughness, is governing the overall toughness of the specimen. That is what we say. That is what is the meaning of this line. Okay, cool. Think about this for some time. Maybe rewind the video or pause and make your own notes. But it is important that you understand this. Now, we make a comparison between the analytical expressions that we derived using the spring stiffnesses and the computational, the actual phase field simulation that we did. So again, we take the block GC bar as 1000 and we choose a toughness ratio in this range. We take it safely as 1000. Say, you can take anything. Now for this GC, you have this GC curve, right? You can always find out its equation using the 2-point slope method. So the equation of this straight line is this. Okay, so from here we get chi as 2169.7. This is particularly for this scenario. Okay, we learned from the previous slide that this GC and this GC bar are more or less same. So we can substitute 1000 here and we can calculate chi. So chi comes out to be 2169.7 and chi is what? Small GC by LC. We can calculate small GC from this expression, which is essentially what? Which is essentially 1. So 1 by LC is equal to 2169.7. LC is this value, which is very, very less, as you can imagine. Okay, it is really less. It is what, like 0.47 microns or something like that. Okay, microns is it, right? I am weak with my units, so don't mind me. Yeah, so we calculate the responses, the stress strain responses. So this red curve is for the actual phase field simulation and this blue curve is for the analytical scenario. Now you might think that these curves do not match and blah blah blah, but the thing is that for the analytical solution we assumed the second order derivative of phi was neglected, right? So those things, they make a difference. The analytical solution is just a one-dimensional solution, and what we are concerned about, this peak. And qualitatively, this scaling, it kind of predicts the same peak as your actual phase field simulation. The actual phase field simulation drops very, very vertically. Why? That's because the layer GC is 1. So it is very, very weak than the bulk GC. So when you apply a displacement load, once it reaches the peak, it drastically drops. So the failure happens almost instantly. Okay, that's why you see this vertical sharp decline. But the stress at which it occurs is qualitatively same. Okay, and same it goes for the phase field simulation. For the phase field simulation, you see this is from Abacus, from our finite element software, and you see if a curve shifts towards its left, if a phase field curve shifts towards its left, we always say that crack propagation has occurred very, very fast, which is evident from this red curve. And this blue curve, we see this gradual increase from 0 to 1. Okay, I hope these two curves are clear, and this example is clear. I will explain one more example. So we observe analytical curves are flatter due to negligence of the phase field gradient, as I said. Now, we look at one more example. All of us, we know the single edge notch tension SENT sample. I have also shown some representative examples of LC in my previous videos, so you are free to watch them. So, we consider this specimen. Take a look at it. We have the edge notch. It is pulled in tension in both sides, in displacement of course, and the origin is at the crack tip. Okay. We have these material parameters. Again, we have E, we have nu, we have GC. GC is what? GC is the material GC. Small GC is the material GC for this scenario. Okay. K sub 1C. K sub 1C is what? K sub 1C is the fracture toughness, or the mode 1 fracture toughness. This is a mode 1 problem, right? From your fracture mechanics, you must be knowing what is mode 1. It is pure tensile mode. So K sub 1C is 23.818 MPa root meter, which is calculated from this value and this value. Okay, so it is what? It is square root of GC into E from your linear elastic fracture mechanics, and UT is T. So we apply a linearly increasing displacement. We did this simulation using 11,000 CP3 finite elements with a mesh refinement of 0.001 millimeter near the crack propagation zone. So we knew that the crack propagation zone is almost here. So the crack will essentially travel straight, right? So we took a region where we used a fine mesh of 0.001 size, and from phase field model parameter identification, so whatever I talked previously, those chi and GC businesses, we calculate this LC to be 0.458 millimeter. Here also we calculated LC, right? We calculated LC as this. For this particular problem, we calculated LC as this. Okay? Now, we first look at the basic LEFM analysis. From the basic LEFM analysis from this paper by Tada, he gives a relation between the displacement formulation and the stress formulation. Okay, because this is a displacement formulation, right? And the expression for your stress intensity factor is always what? Sigma root pi a into some function due to geometry. Okay, again, recap your fracture mechanics, because that is what I'm talking about here. So you have to calculate sigma from this displacement. So U, we know U as T, correct? T is increasing from 0 to whatever time period you are stretching your simulation to, and using this, we know these expressions. This is again a geometric expression, which is this. We can calculate the function of sigma. So sigma is the applied stress for an equivalent stress formulation problem. Okay, am I clear? Next, our stress intensity factor for formula is, as I said, sigma root pi a into some function of the geometry, which for this scenario is this. Now, assuming complete linearity, we can write this scaling. correct? P at u equals to u dash, some u dash by PC. PC is what? PC is your critical load, critical applied load, and Kc is your fracture toughness, and this is your SIF. Okay, so if we calculate sigma, if we know the applied stress, if we know the area of cross section, which is essentially 1 here, okay, 1 into 1 depth, you will be able to calculate P. Okay, sigma is what? P by A. So you know P. Okay, you know K1. How? Using this expression. And you know Kc. The only thing that you don't know is PC. PC is what? PC is the critical load at which this material will show crack propagation. Okay, this scaling, it comes from linear elastic fracture mechanics. We consider this entire problem as linear and elastic. Okay, so we calculate PC. We calculate PC from this expression. Okay, now this picture I showed, I think, in my first video when I was showing a representative phase field simulation. I'm showing it here again. This is what the typical crack pattern of a phase field simulation looks like. You have a band. You see, you don't have a sharp crack. You have a contour, or you have a band. And for the SENT specimen, we expect that the crack will go perfectly horizontal. And this is a variation for different LCs. Okay. Now, as I said, from our parameter identification, our LC was calculated to be 0.458. So we plot this normalized value of stress intensity factor in the y-axis versus the normalized value of displacement in the x-axis. Okay. So from LEFM, which is this expression, we calculated PC, correct? If we calculate PC, we will be able to calculate sigma C. So we will know exactly where to cut the LEFM curve. Suppose if we didn't have PC, the LEFM curve would have gotten straight, would have gone straight indefinitely. Okay, because the LEFM crack, it never propagates, it always stays here. So it is always linear. It is always linear and it does not fall down. It is always linearly increasing. So this green curve, we have to cut it somewhere in order for the crack to grow. Correct? So we cut it at PC. We cut this at PC. Okay? So essentially, when P is equals to PC, this quantity is 1. You can find it out how. This quantity is 1. So that's why we have cut it at 1. And when LC is 0.458, which was found out from the parameter identification exercise that I talked about, the GC by LC or Chi business that I talked about, using this LC, if we do the actual phase field simulation of this problem, we get this curve. You see, there is this non-linearity because of the parabolic degradation function, as I talked about earlier. But what we are concerned about is this peak, is this failure peak. This failure peak, it occurs at the same stress. For the actual simulation, it occurs at a later displacement, but it doesn't matter. What matters is this peak, and this peak is correctly predicted by this scaling, by the parameter identification scaling that I talked about, and it is matching with LEFM. That is what we want. Okay. But if you are more of an aesthetic person, you want sharper cracks and stuff like that. You know how it is with sharper cracks, right? When you make a crack sharp, the peak, it rises. I explained it from this previous curve, right? Let me go back. this slide. Okay, so when you decreased LC, keeping GC constant, the peak increased. Okay, so these LC values are typically very, very small compared to 0.458, but they will give us sharper cracks. So what you can do is, if you are designing a particular material with respect to failure using phase field modeling, what you can do is you can apply the toughness scaling that I talked about. You can do a phase field simulation using the actual LC or the predicted LC from the parameter identification and see if the peaks match with LEFM. Then, in order to make things more aesthetic, you can decrease LC and you can find out your crack paths. Okay. This peak is overestimated. It doesn't matter because you are using the actual LC to design the material. Okay. I hope this is clear. So we observe the peaks of LEFM and the PFM curve with ideal LC match reasonably well. This one and this one. And as LC is decreased, the critical load is overestimated, but we get sharper cracks. So you have to decide what you want to do. If you want sharper cracks, you don't have to use this predicted LC. You can always use a value much lesser than that. But again, if you are designing a material, it is safer to use this predicted LC. Okay. Now I'll discuss some limitations of the phase field model in just one slide. So I talked about the Mehe energy split, right? The anisotropic formulation where you do G of phi multiplied by psi 0 plus psi 0 minus, correct? But are there any other energy splits? So we had this energy split by Mehe that I talked about, I think, in my second video. You can take a look at it, where we split this size psi 0 into plus and minus. So Amor, he suggested one more energy split. What he did is, he took the deviatoric part of the strain tensor, and deviatoric part is what? The deviatoric part is responsible for the distortion of the body, correct? So he split the strain tensor into its corresponding hydrostatic and deviatoric part, and he took the deviatoric part of the strain tensor and clubbed it in psi 0 plus. So essentially this deviatoric part is what is responsible for the deformation. Okay. Here we are taking that only the tensile components of the strain tensor or the positive eigenvalues of the strain tensor is responsible for the deformation. But here we are taking the deviatoric part of the strain tensor which is responsible for the deformation, because the degradation function, it is always multiplied to psi 0 plus. Okay, so the phase field variation which is inside the G of phi, it is multiplied to the psi 0 plus always. Okay, and psi 0 plus contains the deviatoric part of the strain tensor. Okay, hydrostatic is volumetric. So epsilon vol is the hydrostatic part of the volumetric part, and DEV is the deviatoric part. Now suppose you have this problem. Previously we were pulling these two blocks in tension. Now we are pulling these two blocks in pure shear. So what do you expect? These two blocks were rigid, right? So if these two blocks were rigid, they should not deform. They should slide against each other. Correct? This only this middle small layer was deformable, which actually was governed by the phase field, and these two blocks were rigid. So they should slide against each other, right? So Amor, using Amor split, this was happening. Okay, this is taken from the paper, their paper from 2009, and you see that these blocks, they are sliding against each other. But if you use Mehes split, we get this, which is not physical. Okay. So again, it depends on the problem, it depends on the scenario, and it also depends on the material. Suppose you do not have a perfectly brittle material, you have a composite. There you have to research which energy split is actually favoring you. Some energy splits may give you some some really bad spurious cracks, but again, it's up to the user what energy split they'll use. Okay, so this is one of the many disadvantages that I talked about here. So to conclude this entire 3-lecture series, we saw crack initiation, propagation, merging and branching are automatically and effectively captured via the phase field model, and it can be extended to study advanced fracture mechanics phenomena like ductile fracture, fatigue, corrosion, hydrogen embrittlement, etc. Actually, right now I am working on ductile fracture, and if you guys tell me, I will be happy to post some videos on ductile fracture. What I am working on is basically porous plasticity. So you have some porous materials, you introduce plasticity in them, and you propagate your phase field crack using plasticity. But again, those are very, very, very advanced research topics, so I'll be happy to talk about them. Some issues still remain: efficiency versus robustness. So monolithic, which is the fully coupled approach, versus staggered or the decoupled approach schemes. So I talked about the staggered method, that is what we are primarily using in all of these formulations. But there's also this monolithic approach where we do not decouple the phase field and the displacement problem. We solve them, we invert the entire stiffness matrix. Okay, we do not make them diagonal, we invert the entire stiffness matrix. It is computationally very, very expensive, but again, you will be able to make the unloading part of the stress strain response very, very vertical, which is effective for predicting the failure stress or the peak of the response. We have some lingering issues regarding energy split, as I explained in the previous slide, and non-uniqueness of the solution. Non-uniqueness of the solution, it comes when you have a lot of micro cracks. So you will find that for a same configuration, if you do two different simulations, there might be chances that you will not get the same crack patterns in the two simulations. So non-uniqueness always comes, and we have methods to deal with it, but I'm not getting into them right now. Okay, so we end this video here, and we end this 3-part lecture series for basic introduction to phase field model, and I will be back with more topics, and I hope this was good for you, this was interesting for you, and I would bring more interesting topics for you. So bye, and subscribe, leave a like if you enjoy, and see you again.